Hi, everybody. This is Deanna Kosaraju, the founder of Global Tech Women. I want to thank you for participating in Voices 2015, version 3.0 of the annual Conference for Women in Tech, held the week after International Women's Day. So I hope you enjoyed your International Women's Day yesterday, and we continue the party throughout the week with 40 sessions, 25 countries, amazing women who are talking tech and are talking about issues for women in technology on regional, national, and international level. So a couple of housekeeping items. We have a chat window over here on the right-hand side where you can say hello, chat with other people who are online, and also ask any questions that you might have, and we will make sure to get those over to Christine. Christine's talk today is on spatial temporal reasoning over PlayScripts for artificially intelligent characters. And Christy Talbot is with the University of North Carolina, and she's also with Salesforce.com, which Global Tech Women uses for its CRM. So we're glad to know somebody over at Salesforce.com. It's a great product, and we use it a lot. So with that, I'm going to go ahead and launch her PowerPoint. So when the PowerPoint launches, you can drag and drop that PowerPoint anywhere on the screen so that you can have access to the chat window and also see Christine and ask any questions that you might have. So we're going to go ahead and launch that PowerPoint now. So you should be able to see it here on the screen. You can drag and drop it anywhere you'd like. I will be monitoring the chat window, and also if you have any issues, just ping me privately by clicking on my name, and you can send me a message, or you can use the chat window also. And I'll be working here in the background, making sure that everyone is able to see everything and participate. So with that, I'm going to turn it over to Christine.
Thanks, Deanna. So like Deanna mentioned, my name is Christy Talbot. I'm currently a PhD student at University of North Carolina at Charlotte. I also am a program architect at Salesforce.com. So the presentation today is to talk about the research that I've been doing as a PhD student, which is around spatiotemporal reasoning using PlayScripts for AI characters in virtual environments. So you're going to have to forgive me. A lot of this deck is traditionally with a lot of animations, so I've pulled all those out to make it work with what we've got here, as well as a few videos. So we're going to do a little bit of juggling here as we go through. I'll try and make sure I mention which slide I'm looking at to kind of help keep you guys where I'm at within the discussion. So to start with, I want to talk a little bit about what the current state of technology is with virtual characters. So most people are focusing on emoting, on verbal behaviors, and interacting with humans, but the characters typically stand in place or side by side, and they perform very little spatial movement. For instance, Ada and Grace interact with museum goers and answer questions about themselves and virtual characters in a museum, which you can see on slide 3. And also below, you'll see the gunslinger prototype, which incorporates emotional reactions and behavior generation within an interactive application. Other solutions include automated algorithms for spatial navigation or the use of waypoints. However, these are less scripted and more reactive. We want the process to be scripted and on cue, but not too rigid either. So moving on to slide 4, here we show that many games use modularized low-level code to move characters about in an environment. This requires extensive technical skill to translate basic high-level actions, as well as time to write all of that code. Everything is hard-coded on what can be done and when it can occur. Another option that is used today are motion capture files, or mocap files, like you see here from the Avatar movie. They can capture a lot of detail and be very realistic and include facial emotions. However, it requires some expensive tools, appropriate actors, and relevant environments to use this method. It's not very dynamic. Every situation must be recorded for the exact situation you're trying to simulate. It's very hard to pre-record every scenario that could occur. There are other hybrid techniques being researched at universities using these motion capture files, but they still require human intervention to solve the problem. Moving to slide 5. Another newer option uses BML. BML is Behavior Markup Language, and BML Realizers, which take that BML and enact those behaviors on a character that's within the environment. These also require a lot of lower-level coding, but it does abstract and parameterize a lot of the motion. It allows things to be a little more dynamic, since the motions are repeatable and they can be reused. Going to slide 6, here we show that the problem is that the method still requires a writer to write very specific and detailed steps. For instance, here you can see some basic BML which controls 2 characters near the beginning of the graveyard scene in Hamlet. There are 2 gravediggers, one points at the other one, then proceeds with a speech that includes a lot of gesturing and pointing, followed by moving towards the grave. With BML, you have to specify where the character looks, when they look there, how they move, when they move, and when they should pick up and put down objects. This one 10-minute scene of Hamlet took over 4 hours to hand map the BML. This is very time-consuming. Again, not everyone is doing this by hand, but most of those people are focusing on generating characters that stand side by side and talk to each other. Here, we're more interested in where they will be when they talk to each other, as well as their movement throughout a scene. Moving to slide 7. So what do we do? Well, we often give directions to other people on how to get somewhere or how to do something. These directions are often more vague, kind of like what you see on this slide. There isn't specific information for how far to go, exactly where something is, walk in this way, look over here. The bus stop is on your left versus your right when you're moving straight towards it. So the question is, why can't we do something like this for our characters? So if we move on to slide 9, we do something with this with plays. We give high-level directions to the actors for where to go, what to do, and what to say. These are called PlayScripts, as you can see here. We don't have to invent a new way to write spatial directions. PlayScripts are used in almost all theater productions today. Why couldn't we use something like this? Wouldn't this save us a ton of time in writing new scripts for characters in virtual worlds? We believe so, and we've based our approach on utilizing such PlayScripts. So moving to the next slide, slide 10. So what did we do? Well, we took a very famous production of the play Hamlet, starring Richard Burton and directed by Sir Gielgud on Broadway from 1964. We hand-mapped the movements of all the characters in the graveyard scene, as you can see on the top left, and translated them into specific BML commands in 2D. This means we made sure we captured each character's position, where they were looking, what they pointed at, what they picked up or put down, and when throughout the entire scene. This took about 400 BML commands and 4 hours and 12 minutes to do for a 10-minute scene from Hamlet. We use this as our baseline. So I'm going to switch the camera over here, whoops, and see if I can display the video. Alright, so this is the, oh, this is awful.
Here lies the water, good. Here stands the man, good. If the man goes to this water and drown himself, it is willy-nilly, he goes, after that. But if the water comes to him and drown him, he drowns not himself. Arnold, he that is not guilty of his own death, because it's not his own law. That is this law.
So, sorry for the jumbling. But that's the video that we used as our baseline from the Hamlet scene in 1964. So moving to the next slide, slide 11. In conjunction with that video that we also had access to a detailed annotated version of this same Hamlet production, which is a great find for any Shakespeare play. Because Shakespeare plays are notorious for not providing any blocking commands, which has led to a wide array of interpretations of his scripts on stage. So took the script, which was annotated for the movements of characters within the graveyard scene, along with natural language toolkit to parse the character blocking into 2D mappable motions. So we worked with a very simplistic approach that assumed that most statements in a play script are actor, verb, target, and not necessarily compound or complete sentences. For example, we took pointing down into the grave and parsed it into the current speaker as the actor. The action was to point, the target was the grave. This approach of part-of-speech tagging with named entity recognition worked well in translating about 75% of the spatial cues within the script. So we are going to show you one more video that shows that interpretation in 2D. So there's no actual sound with this one. But you'll notice that the arms are pointing out when they're pointing. They've got their little speech bubbles, and the little line inside the circle shows which direction that they are facing at that particular point in time. So this is the same scene that we just saw in the video from 1964. So that was the end of that one. Okay. So then, moving on to slide 13. So we compared the character traces over time for each character throughout the entire scene. We wanted to be in the right section of the stage, looking in the right general direction, pointing in the right general direction, and be carrying objects or placing them in the right area on the stage all at the right time. Looking at the traces that you see on slide 13, we did pretty well. We were able to position the characters in the right place at the right time about 75% of the time. The discrepancies you see from the left, which is the actual hand-mapped video from 1964, and the right, which is using the basic natural language processing method that I showed you in 2D, shows that there are some interpretations that an actor applies to the script that is in the baseline, but it's not available in the annotations for the script. However, with doing as well as we did here with 75% accuracy, we managed to save over 4 hours of time by using this basic natural language procedure and still got the characters doing the right thing at the right time most of the time. Yes, it took about the same amount of time to write the code to do this, obviously, but now we can use this code again for other scenes without additional cost. So moving on to slide 15. So next question is, that's great, we've got 75% accuracy. Now, how do we make it better? How do we incorporate these actors' interpretations to what is explicitly written in the script? One key addition is to better understand some of the implied spatial rules that exist in the theater. For instance, psychology research has shown that the more comfortable you are with someone, the closer you'll stand to them. Also, when you look at larger groups, it's been shown that people will gravitate towards a circular formation to provide a sense of inclusion for all participants. So next we look towards applying these rules, as well as some basic general rules about the theater and common sense, and incorporate those on top of our natural language processor. So looking at slide 16, this is the basic architecture that we utilize with the first set. It takes the play script, it does the natural language processing, it spits out some BML to the BML realizer to control the character within the scene. Slide 17 shows how we're going to apply the rules for grouping of characters, conversational space, theater rules about upstaging other characters, and general rules about looking at what someone's pointing at or looking at who is speaking, and then apply all of those and spit out the BML for that to the BML realizer to move the characters. Looking at slide 18, this describes how the rules engine works. After we've interpreted those annotations from the natural language processor, we can tell what types of actions should be performed by the characters. based on that action, we add additional BML commands, such as gaze or movement, or we make adjustments based on our rules about where those movements should put the character. For instance, when a character points to something, we add additional BML commands to have the other characters look at what is being pointed at. To avoid upstaging, we check a character's end target position for a movement command to adjust the other characters' positions on stage as appropriate. All of these commands, the original ones as well as the added or modified ones, are then sent on to the BML realizer to control the character. So slide 19 shows how this method performed. As you can see here, using that same 10-minute scene from Hamlet, we were able to positionally block the characters very accurately. To accommodate the characters being close enough on stage, we split the stage up into 9 segments, combinations of upstage, downstage, stage left, and stage right, which you can see on the vertical axis. If you take a look at slide 20, you'll see highlighted there is one blip where the rules-based solution and the hand-mapped positioning of characters from the 1964 play do not align. This one spot is where the gravedigger walks towards the audience, turns around, and heads back towards the grave after putting down a lantern. The movement is not annotated in the PlayScript, and therefore it was not performed by our rules-based characters. It highlights one aspect of the actor's initiative to improvise despite the directions provided by the script, and confirms that actors do embellish beyond the PlayScript. However, we are still able to position the characters correctly about 89% of the time, which is up from our previous 75% with just the natural language processing. So we're doing pretty good here. But the question is, moving on to slide 22, is how can we identify what would cause an actor to apply his own initiative to the performance? Maybe there is something about what they're saying that would instigate that kind of additional movement. So we wanted to take a look at all the speech within the play to see if it could imply some additional movements. Not that a person is telling somebody to make a movement, but more that because they're saying something, it implies they should do this particular kind of movement. So here we have a video of, might be caught. Here we have, okay, come on. We have a video of this particular scene where the gravedigger decides to walk forward.
With a crown of stuff on her, it's finding Christian burials and that the only strangers helping her own in the head. Why, it sounds so. It must be seen offendendo. It cannot be else. But here lies the point. If I drown myself wickedly, it aren't using that.
So that highlighted that particular movement, which the gravedigger took upon himself, the actor, took upon himself to make the movement towards the edge of the steps to place the lantern and then move back to continue speaking with the other gravedigger. So moving to slide 23, we decided to look to see if there was some implied motion because of what the character was saying at the time. We were not interested in someone giving instructions, but more whether there was some sort of movement implied because of what was said, how long the speech was, where they were on stage, and when they were saying it. So we took some machine learning and tried to apply it to the actual speech of the play. We took the entire 1964 production of Hamlet, which was the longest running performance of Hamlet at 138 performance, and we hand mapped all the movement with all the speech through the entire 3-hour play. Yes, that was time consuming. So we decided to capture these kinds of information about the speech, such as how long was the speech, how many words, how many repeated words were there, how much punctuation there might have been, how long it was since their last movement, how many of a particular part of speech was used in that speech, and we captured this for the over 3,000 lines of speech within the play. Looking at slide 25, you'll notice that when we did this, about 2/3 of the speech had no movement associated with it at all. So obviously, with machine learning, the smart thing to do is guess that there's no movement with every speech line that is presented to this engine. So we had to take a look at some creative ways to adjust for that that bias with the skew of data. So we tried splitting the different training sizes so it was less skewed with the training set, and we used many different combinations of types of movement, whether it was any movement, a specific movement, big movements, things like that, as well as different phrase sizes or n-gram sizes and combinations of all of these things put together. So looking at slide 27, we used all of that and tried to predict whether a line of speech would have a particular movement associated to it. So looking at this, we took a look at the accuracy, which showed how many were classified correctly. This looks pretty good, but again, it's because the classifiers were guessing no movement, which was 2/3 of the time going to be correct. So we decided we needed to look at precision because we wanted to make sure that if we said there's a movement, that there really should be. And here you'll see we're about half the time accurate. Not too great. Slide 29 shows the Matthews correlation coefficient, which is a fancy way of combining the accuracy and precision to basically say a 0 is performing the same as a random classifier, a -1 is perfectly incorrectly predicting, and a +1 is perfectly correctly predicting. So looking at slides 30 and 31, you'll see for the most part we were doing about the same as random. But since we were able to accommodate 89% of the positioning using PlayScripts, natural language processing, and rules, we really didn't expect to find a whole lot here. It is obvious from these results that there's not a signal related to a person's speech that can account for the remaining 10% of the positioning. These other movements are likely due to an actor's improv during a performance and may be more emotion-based. So moving on to slide 33, to summarize where we left off before we tried to figure out these implied movements, we started with a play script for providing basic high-level movement instructions for the characters within a scene. Using this input, we extracted the spatial movements from the scripts via basic natural language processing techniques, such as named entity recognition and part-of-speech tagging. We fed these movements into a rules engine to incorporate grouping, conversational, theater, and general rules to these movements. Then each movement was parsed into BML commands to move the characters within the scene, providing a relatively low-level control of the characters while utilizing high-level instructions from PlayScripts. So slide 34. So that's great. We did really good. We've got 89% accuracy. We can move the characters around with using basic natural language, but what happens when we introduce a human-controlled character? They may not choose to follow the script correctly, on time, at the wrong time, may not do it at all, or make other sorts of mistakes. So because of this, we want to make sure that they don't look like they're out there doing their own thing. We still want them to look like they're part of the scene and the AI characters are still doing what they're supposed to do as well. So we want to maintain the integrity of the script, but incorporate the human. So looking at slide 35, we decided to look at force-directed graphs to help us with this. Now, force-directed graphs are great for aesthetically placing nodes of graphs in a 2D plane. And it's used for a lot of networks and relationships images. They use forces that interact on the position of each node within the graph, and they attempt to stabilize the forces between the nodes. there's a lot of approaches that exist for laying out a graph on a 2D plane. Our focus was using the Fruchterman and Reingold's algorithm from 1991 because of its use of forces not only between the connected nodes, but also between all nodes in the graph, and its introduction of a pooling function to minimize oscillations. So looking at 36, here's where we start defining what does this graph look like and how does it work to help us with positioning characters. First, we need to represent all of the components of the scene within the graph. So we need to represent the characters by a node. So we've got the green node. Each of the human characters as another node, which will be a fixed node that we won't be able to move, but all of the character nodes will be able to move and adjust based on the forces on the graph. We have a node for the target or the mark or additional pawns within the scene that the character is supposed to move to from the PlayScript. These will not be movable, but the relationships to the characters may change over time. We have some nodes that will pull characters to the audience, so we've got an audience node, and then we have a central grouping point. This particular node within the graph will help with forming circles of characters within the environment. So characters will form more of a semicircle facing the audience as opposed to just forming a general circle. So looking at the relationships between them on slide 37, each node will have specific relationships with each other. The relationships between the human character and an AI character or between multiple AI characters will need to enable a typical speaking distance of about 3 feet. Each character will be tightly tied to their target or mark on stage so we can make sure that they hit their intended position within the scene. And we will want the characters to be pulled towards the audience for greater visibility, so we will add a linkage from each of the characters to the audience. To centralize the group of characters into semicircles, we added the central grouping point, which is the blue point in the image, which will balance itself centrally between all the characters in one direction but be pulled towards the audience in the other direction. And finally, for the human-controlled characters, we'll need the same linkages to this central grouping point to pull all the characters close together, as well as a tie to the audience. Moving on to slide 38, actually 38 through I think 40, we go through some of the different functions that will happen with the graph throughout a scene. So as we add characters to a scene, we need to create the new node and all the linkages to it. So we must create the connection to the audience as well as to the character's target, whether it is a pawn or just a mark on the stage. And if they're the only character on the stage, we don't need to do anything else. If they are not the only person on stage, then we need to create connections between the new character and each character on stage. If they are the second person entering the stage, we will also need to create our central grouping point and connect both the new character and the other character to this point. If they're not the second person, that point will already be there, so we just need to add a connection to it for our new character. If more than one character is entering the stage at the same time, then we need to introduce a stronger connection between the two characters as they are more likely to remain closer to each other initially. When a character leaves the stage, some basic cleanups are needed, such as removing their audience node, removal of their target node and connection, removal of their node as well as all their connections to the other characters. And if only one person remains on stage, we have to remove that central grouping point as well. When a character moves, we need to remove any remaining linkage to previous marks on the stage and create a new linkage to their new mark on the stage. Initially, these target connections will be strong, but will weaken over time to simulate the lowering importance of that mark as time progresses. The character's audience node will also need to be updated to ensure appropriate forces are being applied. We'll need to recheck the arrangements due to any human positioning with respect to the requested movement of the AI character and make any adjustments as needed as well. The special case here is when the human moves. At this point, we need to update the audience node just like the AI characters. However, this will signal a reorganization of the characters to ensure appropriate positioning due to the human's location. All forces will be reevaluated for a new equilibrium state, and AI characters will adjust while the human character is moving. This will not create a connection to a target or mark location for the human, since we cannot move where the human resides on the stage. Looking at slide 42, this shows the forces that we use for each of the relationships between the nodes. So when we have the AI characters connected to each other, we want a typical conversation space of about 3 feet. So we have both attractive forces to pull them together as well as repellent forces to ensure that they don't get too close together. The attractive forces are made stronger between two characters whenever they enter the stage together. However, this attraction force will reduce over time to the standard AI character forces. With the humans, we want the characters pulled towards the human, but not as strongly as to each other, just in case the human is way off, doing their own thing, and not following the script very well. We want the characters primarily to reside within the front part of the stage, but not too close to the edge either. So we will add a force that pulls them towards the audience, but keep them in the front half or quarter of the stage when possible. The center point will also be pulled towards the audience, but more strongly, to ensure the groups are facing forward and form a semicircle. The center point will also pull each character towards an even spacing around this point, and the character's marks will pull strongest of all without any repelling. So looking at slide 43, there are different aspects that need to be evaluated to fully vet these techniques with the force-directed graphs. First, we need to determine if the graphs can produce an optimal or semi-optimal arrangement based purely on the relationships between the characters, targets, and audience. Secondly, we need to evaluate how this optimal arrangement works over time through an entire scene. In other words, do the characters make too many movements because of the human factor? Do the characters oscillate between positions? How do the characters' relationships adjust over time within a scene? Finally, we need to evaluate how realistic and appropriate the positioning is from a user's perspective. This could include a director, theatergoer, gamer, and so forth. This will be the ultimate evaluation of whether this approach, in conjunction with our prior work, can position our characters in a realistic and reasonable manner. So looking at slide 44, we start with a random positioning of characters and their relationships on stage. This does not necessarily represent actual locations on the stage for the characters, but is mostly an initial representation of their relationships, so we can verify what our force-directed graph will do with those relationships. With slide 45, we show that the human character decides to move, and with that, we trigger the graph's repositioning using the force-directed graphs. Slide 46, once that evaluation is done, we end up with a nice arrangement of the characters that is balanced, facing the audience and in a semicircle. All of this while maintaining a reasonable distance between each of the characters, as well as character C's mark on stage. So looking at this point in time evaluation, we wanted to look at whether the graphs can produce an appropriate arrangement based purely on the current relationships. So the criteria that we used were around even vertex distribution. We want to make sure that they're evenly distributed, they're not all clustered together. In order to use the algorithms that we had for force-directed graphs, we need to make sure that we'll have a small number of vertices to ensure it can run properly. We need to make sure that using fixed vertices do not impact the movable vertices within the graph. And finally, the centering and circling of groups to make sure that the characters are forming semicircles when they are more than a couple of characters on stage. So we took randomized relationship scenarios and evaluated each of these items to determine the force-directed graph effectiveness. We saw that the characters were evenly spaced on the stage. We had up to 40 vertices with 12 characters on the stage, and characters remain close to their marks and form semicircles for the characters. So this was really good. Looking at slide 49, we wanted to incorporate these force-directed graphs with our previous architecture, determine how this performs through an entire scene. So we have the natural language processing that has the actor-verb-target, which the rules engine takes, applies some additional rules to those commands, and then feed that into the force-directed graph for any adjustments that need to happen because we've got a human-controlled character in the mix. Looking at slide 50, the question is, how do we evaluate the force-directed graphs work within a scene? So first thing that we looked at was occlusion. So one of the key components of theater is that you don't occlude other actors on the stage. So we want to minimize the amount of occlusion of each of the characters by another character throughout the scene. Second piece is we want to make sure that the characters have some sort of grouping or clustering on the stage. The goal is not necessarily to utilize the entire stage, but to ensure that all the characters appear to be in collusion with each other. We don't want one character to be hanging out in one corner, the rest at the other side of the stage. So we're looking to minimize the amount of space the characters occupy, keeping in mind the need for conversational space. Looking at slide 51, to evaluate this, we applied our force-based approach to an entire scene of Hamlet. We calculated the amount of occlusion and clustering found with various cases. We started with a baseline run, which utilized the hand-mapped blocking from the 1964 Hamlet production on Broadway. And we can see that we have some minor occlusions of the characters on the stage with that production, as well as a fair amount of clustering in both dimensions of the stage. When we took one of the characters and made it a quote-unquote human by randomizing their movement, you see that not adjusting for that human's movement, we end up with less clustering and more occlusion of the characters, the greater the randomization was. So line 3, where we've got the quote-unquote human performing accurately only 10% of the time, we've now increased to about 30% of the stage being utilized in both directions for all of the characters. Now, when we take a look at placing the 3 characters in a horizontal alignment with conversational space, we'd expect to see about a 28% clustering. So there's less clustering of the characters or inclusion of the human when nothing is done to compensate for the human's incorrect movements. So looking at the next scenario on slide 52, we used our forces and did the same thing, chose the same character to randomize its movement, and you'll notice that we have less occlusion, and it's also consistent throughout all the scenarios, as well as the clustering remains consistent throughout all the scenarios as well. So regardless of what the human is doing, we're still able to make them part of the movement on stage, regardless of whether they're doing something correct or not. So moving on to slide 54. So to recap, what we've done is we've evaluated the force-directed graphs, point of time, as well as throughout an entire scene. So now we need to look at some qualitative evaluations. And what we've done is created a user study to compare the baseline production to our natural language processor component of our algorithms. And we took a 15-minute video which enacted the graveyard scene from Hamlet within the block world, which I'm going to show you in just a second. Some people were presented the representation of just the hand map performance from 1964, while others were presented the natural language processor representation of the same PlayScript, the one that we were able to match 75% accuracy. We used a block world to avoid any bias of character representation and to enforce a greater focus on the spatial aspects of the performance. So this is what the scene looked like.
There is no hate in gentlemen, but gardeners, ditchers, and grave makers they hold up Adam's profession.
Was he a gentleman?
I was the first that ever bore arms.
Why? Have none.
But, Artie, how dost thou understand the scripture? Scripture says Adam did. He did without arms. He'll put another question to me. Thou answerest me not to the first. Guess thyself.
Who to?
So that's a little snippet of what the video looked like that we had the users use. Taking a look at slide 55, this is a listing of the questions that we presented to the users. These came from judging criteria that are used in one-act plays at both high school and collegiate levels. We intentionally included both positive and negative versions of the questions along with different wording to avoid any bias on question phrasing. Shown here are also the listing of the expected correlations of the different questions. However, we found very little significant correlation between the questions during our actual study. Additional questions were presented to help identify appropriate demographics as well as open-ended questions to assist with other information not captured with the Likert questions. Looking at slide 56 and 57, the questions were presented in a randomized order after viewing the video, but only if they knew the color of the intermission screen, which appeared halfway through the performance, and if they had been on the video page long enough to actually watch the entire video. This helped to ensure that participants actually viewed the video before completing the survey. So we ended up with 748 people trying to complete the survey, but only 214 completed it because of these checks that we put in place. And most of these did not have a statistically significant difference. There are a couple that did, but they are very minor. So you'll see here we've got one on the consistent movement and on character emphasis. But again, these were so minor that from a practicality perspective, they're really not useful. There were also some slight differences with respect to the demographics, such as region, age, gender, culture, and such, but this may mostly be due to one or two users evaluating it differently than everybody else, and most of the participants that participated experienced some sort of fatigue with watching a 15-minute video that had very little action in it. This was also noted in some of the open-ended responses, saying that it was boring and slow. So we'll be taking that feedback into consideration in our future user studies. Moving to slide 59. So these are all the things that we've done to date. Slide 59 highlights where we see this work headed, what's left to be done, at least as far as completing my dissertation for my PhD. Firstly, we've got a continuation of the user studies with a shortened video to avoid the fatigue issue that we saw in our first user study, which would evaluate not only the different components, the baseline, the natural language processing, plus the rules, plus the force directed graphs, but also a randomized scene to ensure that our surveyed questionnaire can capture a poor performance. Also looking at doing some additional human interaction user studies, which would have the participant perform as a human and see what their perception is of the scene using the baseline versus our consolidated solution with the force-directed graphs. And lastly, looking to expand and generalize these techniques on more than just the play that we used from 1964. So identifying different play types based on how they're organized and apply and evaluate these same techniques for many more of the plays. So slide 61, to summarize, it's challenging to position characters in virtual environments. Current work requires a lot of time or technical expertise to produce realistic positioning of characters. We introduced the use of PlayScripts for a high-level instruction set for virtual human characters. We next applied some basic part-of-speech tagging and named entity recognition to extract the spatial movements from the PlayScripts. We introduced some basic rules to adjust the character positioning, thereby allowing us to replicate 89% of an actor's movement. We looked to identify a signal within the character's speech that might imply movement within the scene. Next, we incorporated human-controlled characters. To do this, we introduced algorithm structures and forces for incorporating a human-controlled character within a scene. To qualitatively evaluate the performances, we created a spatio-temporal survey based on one-act play judging criteria. Then we performed our first user study to evaluate both our questionnaire and our natural language processor approach. And finally, we reviewed the planned work to complete this dissertation. And that is all of it. So slide 62 shows some of the publications that have highlighted this work. And I can open it up for any questions.
That was an amazing talk. Really incredible work that you've been doing. How long have you been working on this?
I'm starting on my 4th year for my PhD.
Okay. You've made such great progress in that short time. It's really amazing.
Thank you. It's been a lot of fun.
Does anyone, yeah, it looks like it. Does anyone have any questions? Okay, I guess not right now. They're probably contemplating. It was a lot of information. So do you have a background in drama? I mean, how exactly did you, I mean, it's a great cross-section of drama and technology. How did you come across this idea?
It kind of started with my advisor. We were looking at something in the behavior area, and we just kind of stumbled across it. My advisor has a little bit of history with the theater. I really don't. So a lot of this has been new for me, and I've been collaborating with some folks in the theater department, as well as specifically with Shakespeare experts as well. So I've learned a lot with it, and I do have to specify that all of these things are specific to one particular type of theater arena. Other arenas are going to have different rules and different setups, but you know, as far as this proscenium stage, these all seem to apply very well.
Well, it's fascinating. I love when technology crosses other disciplines. I think that's when real innovation happens, and this is proof of that. So thank you very much for this great talk. And I agree with Linda, it was a great talk. If anyone has any questions, feel free to reach out to us. You can post on the Global Tech Women Facebook group or on Twitter, #Voices2015, and we'll get your questions answered. We are taking a break for 1 hour, and then we will be back with a CEO who has developed a platform for parents to keep track of their children's grades and interact with their teachers. It's quite an interesting technology and a great idea. So we hope that you'll come back in 1 hour. Thanks so much, Christine, for everything.
Thank you.
Appreciate it. I'm sorry about the video issue. You actually resolved it. I mean, it turned out really good. So I know it was a pain for you, but it worked out really well.
Yeah, that's good. I figured worst case, that's what I could do. So I have a few extra monitors.
All right, awesome.
Thank you.
Okay, thanks everybody. We'll see you in an hour. Bye.